All right. You guys hear me? Sounds like it. Cool. How's it going? We're back. More computer vision. Yeah. I still have my little pointer thing. Oh, let's see what. There we go. I'm so excited about this pointer. It's very fun. All right. So just some logistics stuff. Homework 1 is out. It's due on Thursday again, as usual. Your grades are out for homework 0. If anyone has any questions about grades or anything, you can come talk to me or message me on the little thing, or message Kiana. She's the one who did all of the grading for the assignment. So yeah, look through your homework 0 grades. If you had any issues with it, you may want to fix them because you're using the same code for homework 1, and some of it is important. A lot of it doesn't matter very much, but some of it you're going to want to be right so that you can do homework 1. And that's going to keep being true sort of moving forward. You want to make sure your homework, if your homework isn't correct and you don't want to fix it yourself, come talk to me and I can give you one of the solution files so that moving forward you're not using bad homework to keep doing bad homework. Anyway, all right, so what did we talk about last time? We were talking about this resizing operation, which you guys, I think, are doing for this homework, right? Yeah. So talking about basically our algorithm for resizing images. We want to make our new image match up the 2 coordinate systems of the image, loop over all of the points in our new image, and do some kind of first mapping back onto our old coordinate system, and then some kind of interpolation. We talked about how we do bilinear interpolation, how that whole thing works out, and how we fill in basically the rest of our new image. So you guys are working on this right now. Hopefully the slides and sort of the material for the assignment make it pretty clear how we're going to do all of this interpolation and mapping between coordinate spaces and stuff. And we talked a little bit about different methods of doing this interpolation, where we have, here we have, we've got to be facing the right direction so this works right. Let's see, we have nearest neighbor. We have, I think, different versions of bilinear, so more pixels and fewer pixels, and then some bicubic interpolation and nearest neighbor over here. Nearest neighbor just ends up looking real weird for this. And we talked about how interpolation, if we're going to do really big changes to the image in terms of making it smaller, I don't really know the right way to phrase that. If we're going to do a resize operation that makes the image a lot smaller, oftentimes interpolation is not what we want. What we really want is some kind of local averaging of pixels in some neighborhood. And the way we do that is with a convolution, which is just a weighted sum over pixels. But it turns out, convolutions are actually a lot more general than just doing sort of this averaging. They can be used for a variety of applications. So we have all of these different kind of filters that do all sorts of different things. And we talked about a lot of them last time. You guys will probably recognize some of your favorites up here, and we'll talk about them a little bit more this class. So get ready. So this class, we are going to be talking about edges and feature extraction. And we'll still be talking about features probably next class as well. We'll see what kind of stuff we get through. So just a quick note, this actually is sort of important, so you guys should know a little bit about it. There is a small distinction between basically cross-correlation and convolution operations. So both of them, you are basically taking 2 images and performing some operation with them. In cross-correlation, basically you just apply the filter in the way that it's presented to you. And in convolution, you're going to rotate the filter by 180 degrees or flip it basically along its vertical and horizontal axes. And I'll let you guys work out on your own why those are the same operation. Actually, wait, we can do it. Piece of paper. OK, piece of paper, flip it vertically, flip it horizontally. Oh, it's just rotated. So it's the same thing. So in the homework, you guys are going to be doing cross-correlations for everything, even though we're calling them convolutions. And in practice, a lot of people just do cross-correlations and just pretend like they're convolutions. They actually have a few sort of not as nice mathematical properties of convolutions. So in general, we're going to be talking about convolutions, and those are sort of the nice version of these 2 methods of applying filters. In both of these scenarios, we're applying a filter. In one, we're just rotating it a little bit. So it's not like a huge distinction, but you guys should know in your head somewhere at some point that convolution is the one where you have to, man, sometimes this thing just goes weird. Convolution is the one that has the nice properties, and you have to rotate the filter. And cross correlation is the easier one because the filter is already the right direction. So do that one for the homework, but those are the good ones. So what can we do with these convolutions? What's the deal with them? Mathematically, we have a lot of nice things about convolutions. So they're commutative, which means that taking the convolution of a filter with the image is the same thing as taking the convolution of the image with the filter. Or if you have, maybe you want to do a convolution of two filters on the same image. So maybe you want an image and you want to convolve with a filter, and then you want to convolve the result of that with another filter. It turns out you can just convolve the two. You can convolve the two filters together first, and then convolve that with the image. So that's this associative property here, where we can basically switch around the order of doing these convolutions. We also have some nice properties about distribution over addition. And usually you're not distributing into addition. Usually you're using this to factor out some common elements so that you can add together some stuff first. And we'll see some examples with it. And also just sort of it does kind of what you would hope or expect it to do with scalars. And that's because we're just sort of multiplying things together and adding them up. So a lot of these properties work out nicely, which is cool. This means that a lot of convolutions will decompose into different parts, and this can be useful too. So for example, the Gaussian filters that you guys are doing, you could actually implement that as, if you have a 7x7 Gaussian filter, you can actually just decompose that into a 1x7 and a 7x1 sort of one-dimensional Gaussian filter, and run each of those over the image independently, or sort of one after another, and do your smoothing in that way. And just from doing some of these decompositions, you can save some mathematical operations. So in practice, you can do some cool things using these mathematical properties that are pretty nice. There's a lot of other filters. I think most of the ones that we've talked about before. So if we look at our filters here, I think a lot of these will decompose into different parts. So for example, this filter will decompose into -1, 0, 1, and 1, 2, 1. So basically these two components. It's not as big of a win decomposing a 3x3 filter into a 1x3 and 3x1 filter. It's nicer when you have sort of these really big filters that you're dealing with and you can decompose them a bunch. So that's cool. So what can we actually do in terms of applications of these convolutions? It turns out just a ton of stuff. So you guys have already seen blurring and sharpening. And today we're going to talk about edges and features and derivatives a little bit, but also just all of sort of our operations that we talk about in computer vision, or all of kind of the big problems that we're dealing with are solved using mostly just convolutions of filters and then some little intermediate processing. So things like super resolution, if you want to make an image a lot bigger, but still maintain some of the detail in it. All of the applications that we talked about in terms of classification, detection, image captioning, just tons of different stuff are just built on top of these really simple building blocks. Basically, everything that we do in computer vision is just using these convolutions to extract features or just do the whole process for us, basically. So let's talk about edges, because oftentimes when you're looking at images, you want to know something about what's going on in the image. And edges tell you a lot about what's going on in the image. They can denote basically different objects. They can denote some sort of important scene concepts, things like that. So often it's important to find these edges and then do some sort of processing using them. So we talked about before, images are basically just functions. And the function basically takes some two-dimensional xy point and maps it to either a value if you're talking about a grayscale image, or maybe 3 different values if you're talking about RGB, some sort of mapping from basically a spatial location to some values. And edges in this function are just areas of rapid change, basically. So you can really see it when we start plotting this stuff out in 2D. The edges of the wheel and of sort of the components of the bicycle are really apparent, especially in the picture sort of on the right here. We can see, the areas where this function is changing really rapidly are the things that we think of as edges. So in one dimension, this basically looks like, you have some area where there's not a lot going on, which isn't really pictured, some area of pretty rapid change, and then another area where there's not a lot going on. So it's just some location where there's some rapid change in this function that we're talking about. So we want to be able to find these edges in the image, and one way we could think about doing that is just taking derivatives. Hopefully you guys sort of have taken some calculus and understand derivatives. What we're going to get out of the function on the right that we have over here when we take the derivative is this sort of peaking function where the highest point on that function is the area where the function is changing. The peak of the derivative is the area where the function is changing the most. So we could imagine that we just sort of take the derivative of an image and we say anywhere where this function is sort of really high, anywhere where there's like a large response, that's probably an area where there's some kind of edge going on. And so that's in like the continuous space. You can talk about taking derivatives of functions where you actually can write out some closed form of the function. We don't have like a real function, so we have to kind of estimate. And in general, we're going to use sort of our definition of what a derivative is, where it's just the limit as some h goes to 0 of f of a plus h minus f of a divided by h. And really, this is just saying, look at the function at a spot, and then move over a little bit and look at the function there, and then divide by how much you moved over. And it's sort of the slope of the line between those 2 points, basically. And usually, you want the limit of this as your distance that you're moving goes to 0, but we can't really do that with images. So what we're going to do is, one possibility you might think about is what if we just set h equal to 1? So instead of taking the limit of this as it goes to 0, let's just look at 2 adjacent pixels. And what this will look like in practice is just a convolutional filter. So all we want to do is have a negative component of 1 right at the place where we're trying to take the derivative, and then move over by some amount. In this case, we're going to set h equal to 1, figure out what the function corresponds to at that location, and subtract one of the values from the other. So we're going to look by over 1 pixel, what's the value there, and then subtract out the value of the current pixel that we're looking at the moment. So this is one potential way that we could imagine taking derivatives of an image, or sort of estimating the derivative of an image. Now, there's some problems with this. You guys may have started running into this with the homework. If you convolve an image with an even-sized filter, sometimes sort of weird things happen. This also means that really kind of the area that we're taking the derivative of is sort of this intermediate area instead of looking at the derivative of this actual pixel. So instead, we might want to think about setting h equal to 2 and basically looking at either side of the pixel that we actually care about and fitting a line between the 2 neighbors of that pixel. And what that will look like is basically, again, we're going to set h equal to 2. So we're going to have this component where we're dividing by 2 or we're multiplying by 1/2. And then we're going to look at the pixel to the left of us, and that'll have a negative component, and the pixel in front of us, that'll have a positive component. And this will give us sort of a rough estimate of what our gradient is at this pixel location. And this is just in the x direction. And obviously in the y direction, we have basically the same corresponding filter. So one problem with this is we have a lot of noise going on in these images. So they're not these like nice smooth functions that we're used to taking derivatives of. And this can cause problems especially in small areas. So if we're just looking at like 2 or 3 adjacent pixels, we see over here basically like there's all of these kind of like weird little spikies going on and stuff like that. And also if you're just kind of out in like a flat area of the region where there's maybe not a lot going on, say in sort of this region, you still have some little noise. You have some like spikes in this function. And your derivative is going to pick those up. And it's going to kind of think that maybe those are edges because there might be just some like speck of dirt on the ground or something, and there'll be some big abrupt change in this function, and the gradient will be really high there. So we want to figure out some way of basically getting rid of some of this noise. And we actually already know how to do this. We have these Gaussians that we talked about that we can use for smoothing this function. So in practice, when we actually want to take these gradients of an image, it's often good to use a Gaussian filter to smooth them first. So you see that basically when we take this Gaussian over the image of the dog, when we look at just sort of a very small portion, instead of having all of these little spikies, we have a much smoother function. And when we do this kind of smoothing, it means that when our derivative responds really highly to an area, it's much more likely to be a real edge than just some noise in our function. I think I have this slide in there twice. So what we want to do is smooth our function, smooth our image first, and then take the derivative of it. We talked about Gaussian smoothing last time, and in practice, this is basically a pretty decent estimate for a little 3x3 Gaussian filter. What you would really want to do is basically take some normalizing factor over that 3x3 filter if you were actually just going to use that as your Gaussian filter. In practice, when we're talking about derivatives, we are really just sort of looking at the relative derivatives of different places in the image. So multiplying by scalar factors doesn't matter too much. We're just going to be looking for areas of high response and areas of low response. So, we have our derivative in the x direction, and we have our little Gaussian smoothing filter. So we're going to, as we talked about, smooth the image first, and then take the derivative of it, or estimate the derivative with our filter. But we talked before about all these nice mathematical properties of these convolutions that we have. So we can just use our associative property to instead first convolve the gradient filter that we're using with our Gaussian smoothing filter. And we can go through this process of basically applying this gradient over our Gaussian. And we have, here 0 plus 2, and we have -1 plus 0 plus 1 is 0, et cetera, sort of moving through this filter. And we end up with 1/2 times this filter, which when we multiply it through is just our Sobel filter. We learned about this last time. So what Sobel filters are actually doing is this combination of a gradient in a direction with this smoothing function. And in general, this is, this particular one is called a Sobel filter because I think some dude named Sobel came up with it. But we're really just doing a gradient of Gaussian operation. So in general, sort of the general case looks like this, where if you take a Gaussian function and you take the derivative of it, you end up with some function that looks like that. And then we're estimating it with some kind of filter, basically. And you can sort of tell that our filter actually looks, our sort of discrete version looks a lot like the continuous version, where we have this area sort of in between the two peaks where there's 0. We have this kind of curve where we have maybe a negative response, but it's kind of lower. Or sort of there's this peak negative response right in the middle, and then these negative responses that aren't as sort of extreme. It looks a lot like what our actual filter looks like. And again, sometimes this Sobel filter can basically be, I think before we talked about Sobel filters, they were basically the negative version of the thing on the right side of the screen. And when we're talking about gradients, multiplying by these scalars don't actually matter a whole lot because we can just sort of think about flipping the direction in terms of how it's measuring the gradient. Everyone sort of clear on derivatives and Gaussian smoothing and where these Sobel filters come from? Any questions about that kind of stuff? So we talked about how this is cool. We have kind of this combined smoothing and derivative operation. And now we can run this over an image and get basically a smoother estimate of our gradient, something that's not as affected by some of the noise that might be going on in our image. And in practice, we have a Sobel filter both for the x and y direction because we probably want since this is a two-dimensional function, we want some estimate of both halves of the gradient. But edges go both ways, so it's often not enough just to look for sort of the extreme points in our gradient that we're going to estimate, or it's not enough to look for sort of the high points in this gradient that we're going to be getting out of the image. What we really want is to find both extremes. We want to find places where the gradient is really high, and we also want to find places where the gradient is really low. So in practice, instead of thinking about gradients and first derivatives, we can think about second derivatives. So in one dimension, second derivatives have this really nice property where anytime there's a peak in the gradient, the second derivative will cross 0 at that peak. So now, instead of looking for basically really high responses or really low responses to the gradient function, we can just look at places where the second derivative crosses 0. And in practice, this might be a little bit easier to sort of look for in our image, and we don't have to worry about looking for both positive and negative components. We can just look for these 0 crossings. So that's in one dimension, and things get a little bit more complicated when we go into 2 dimensions, but we're going to use this measure called the Laplacian. And basically, this is the sum of the partial derivatives with respect to x and respect to y, or the second partial derivatives with respect to x and respect to y, and you just add them together. And we'll talk about why this makes sense in a second. But first, when we're talking about the Laplacian, we need some way of estimating basically these x and y components of the second derivative for our image. And we're going to do the same thing that we did before, where basically we have our definition of the second derivative. And in particular, it has these 3 components to it. It has basically the function a little bit ahead of where you are right now, the function where you are right now, and the function a little bit behind where you are right now. And we have these pretty simple components of just, it's going to be 1 times the function on either side of you and minus 2 of the function right where you are right now. And in general, we want the limit of this as h goes to 0, but we're not going to do that. We're just going to set h equal to 1 again. And we have these discrete estimates for what the second derivative is in the x and y directions of our function. And in particular, there's sort of these filters that we see down here. So we're not actually using the second derivatives themselves. Instead, we're going to use this Laplacian that we just talked about. And the Laplacian is this sum of the partial second derivatives just in one direction. So either the second derivative with just respect to x or just respect to y. And what the Laplacian actually is it measures the divergence of the gradient, which is the flux of sort of the gradient vector field in a small area. And we're going to talk about what this means, because I had to learn a bunch about this yesterday in preparation for this. So now I have to impart this knowledge on all of you. So we have this edge in the image, and we're going to assume that we've already done some kind of smoothing to this image, so it's not just like this really abrupt change, but it's actually kind of like what you would sort of see is like a blurry edge, basically. There's a large portion in one part where there's not a lot going on, and then there's sort of this gradient that changes really quickly, and then there's this large portion that also has not a lot going on. And we can first imagine taking the gradient of this image, and the gradient is going to be this vector field, where the vectors are going to point in the direction of the largest change. And they're going to point toward basically getting steeper in terms of this function. And the magnitude of the gradient is going to be how fast the change is actually occurring at that location. So you notice that in the top left, basically, there aren't any vectors because there's no change going on. The vectors are just sort of these 0, 0 things that aren't pointing anywhere. Same with sort of the bottom right. And then in this gradient, we have the same thing going on, where basically at the start of the gradient, there is a little bit of change. There's a little bit of a gradient pointing sort of uphill. As we get toward the middle of the gradient, that's where the rate of change is fastest, and that's where we have these largest gradient vectors that are sort of really strong. And these are all pointing in the same direction, because the gradient is only going in one direction in this example. And then as we get toward the end of this edge, we have these smaller and smaller gradients. So what the Laplacian is measuring is the flux of this gradient field at some really small point, basically. And what we can think of that is if we take a little straw or just take a little circle and look at this in one location, how much of the gradient field is sort of flowing into that circle versus how much is flowing out of that circle. So if we look at anywhere kind of in these areas where there isn't much going on, the flux is basically going to be 0. And this is fine. There's nothing going in. There's nothing going out. So there's not really any flux in that little circle. If we're sort of somewhere near this gradient coming in from the top, we have a little bit of gradient flowing into this circle, and we don't have anything flowing out of it. So this is going to be an area of positive flux. So this is going to be a location where the Laplacian is a little bit positive. And then as we get towards sort of the center of this edge, we have some really big gradients, but in general we have basically the same amount of gradient vectors flowing into this circle as we have flowing out. So the flux is actually going to be 0 again here, and then as we move again towards sort of the lower right-hand corner of this image, we have a few vectors going into this little circle, but we have a lot more of them leaving this circle, so our flux is going to be negative. And in general, this is actually going to look a lot like our second derivative in one dimension, where we have these areas as we go toward this edge where the second derivative gets really high and then crosses 0 and goes negative and then goes back to 0 again. So the thing that we really care about with second derivatives in one dimension or with Laplacians in 2 dimensions is where the Laplacian crosses 0. So in practice, we want to do some sort of estimate of the Laplacian, and we have our 2 kind of filters that we came up with to do estimates of the Laplacian or of the second derivative in one dimension. And the Laplacian is just adding together those 2 components. And so over here we have basically the result of this convolution will give you the second derivative in the y direction, and the result of this will give you the second derivative in the x dimension. And we want to add these 2 together to get our Laplacian, but we can take advantage of our cool mathematical properties of convolutions to say that instead of doing these 2 separate convolutions, we can just add together these filters and then do the convolution of that addition with our original image. And we can sort of pad these out with zeros to actually be able to perform this addition, and we get a little filter that looks like this. So this is probably familiar to you guys already as well. This was sort of our little edge detector that we talked about last time. I think, again, this is actually just the sign flip of our filter that did edge detection last time. And that's fine. Again, we can just kind of flip around the signs of these things, and all we're looking for is 0 crossing. So we're just looking for points in the image where we went from positive in one place to negative in another place. So it's not a huge deal that this is sign flipped. You can basically use the filter in either sign. And so if you think about why the filter, so again, we talked about the Laplacian is going to detect the edge where it crosses 0, but we've already been using this filter to detect edges, and we just said that anywhere where this filter was sort of large, that was an edge. And this actually kind of makes sense if we just go back really quickly. Anytime there is an edge, this second derivative is still going to have basically a really large peak and a trough. And the peak is going to be on one side of the edge, and the trough is going to be on the other side of the edge. So what we were doing before when we were just convolving this filter with an image was finding one side of the edge or the other side of the edge, depending on what sign our filter is. But what we really want to do is find the middle of the edge. So that's why we're actually going to do this convolution and then try to find these 0 crossings in practice to find edges. But that's why this filter was already sort of working a little bit to find edges, because we have a filter that basically responds to edges pretty strongly, both positively and negatively. So in general, the filter with sort of the -4 in the middle is called the negative Laplacian, and the filter that we were already talking about before is called the positive Laplacian. And in practice, we want to do some kind of Gaussian smoothing beforehand. We're talking about second derivatives, and second derivatives are really sensitive to noise. So in general, we want to do a lot of Gaussian smoothing to get rid of a lot of that noise first. So we make sure we're just looking at things that are actually edges in our image. And again, we can do this same sort of process where we want to smooth with a Gaussian first and then apply this Laplacian filter. And in practice, the way you do that is you just apply the Laplacian filter to your Gaussian filter, and then you end up with this, it's called Laplacian of Gaussian, or log filter, and we use that to run over the image to get this smooth estimate of the Laplacian. And you can get pretty good approximations of this with some sort of largish kernels that, usually like 7 by 7 or 9 by 9 kernels. So that's cool. And this is something that will come up again when we start talking about looking for good features and stuff like that, is doing this Laplacian of Gaussian. So just kind of keep it in mind. And in practice, what it looks like is people sort of talk about like an inverted sombrero or something, where it's like this little, or an inverted hat, where it kind of starts going up a little bit and then goes down. So we're looking for edges, and we might, not want to do second derivatives because we're scared of them for some reason or something. So instead, we can sort of think about an image as a function again, and we can think about doing Fourier transforms on this image. So if you guys are familiar with Fourier transforms, it's basically this idea that if we have a function, we can decompose any function into different parts that are sort of high frequency oscillations and low frequency oscillations of sine and cosine waves. So what we're going to imagine is basically edges are high frequency changes in our image. And what we really want is some sort of filter that only responds to high frequency changes. And in particular, we can imagine sort of different edges will be different frequencies depending on how wide they are. So really small, sort of fine detail aspects of images are generally very high frequency changes in the image, whereas like really large changes in image, like areas where you transition from one color to another, or really large edges in an image, might be more low frequency changes in the image. And we might want to look at these kind of different aspects independently. So we'd really like some way of kind of splitting up the image into its different frequency components. But maybe we don't really want to do Fourier transforms because that's confusing. So we're still going to be thinking about this in terms of just doing filters. And in particular, how we're going to think about it as a difference of Gaussians. So we talked about Gaussians before as basically this smoothing function. And what a Gaussian really is this low-pass filter that's going to get rid of high-frequency information. It's just going to sort of go over the image and leave all of these low-frequency changes. And in particular, you can figure out, based on the size of the filter that you're using, based on the sigma that you're using for your Gaussian, what components are actually going to be let through this filter and what components are going to be thresholded out or sort of reduced significantly. So if we take the Gaussian filter of some image, we get left with just the low frequency components of that image. So what we can do is take our original image and just subtract out the low frequency components. And when we do this, all we're actually left with is just the high frequency components of that image. But in particular, we might want to look for sort of specific bands of frequency in our image. And that's where this difference of Gaussians comes in, where we can take two different Gaussian filters that use different sigmas and filter the image by them and take their difference. And what we're going to be left with is just sort of the frequency ranges that fall in between those two filters. So again, we have sort of these nice mathematical properties where the thing that we're going to be doing is basically running this Gaussian filter on an image and then subtracting it from another Gaussian filter run on the same image. But that's equivalent to just subtracting the Gaussian filters from each other and then running that result on the image just one time. So this is nice because we just have to run a single convolution instead of running these two convolutions. And it's pretty easy to subtract Gaussians from each other. So what does this difference of Gaussians actually look like in practice? We have here our Gaussian with sort of a wider standard deviation or a larger variance. We have a more peaky Gaussian that has a lower standard deviation. And when we subtract one from the other, we basically are left with this same kind of structure that we were just looking at. It actually sort of looks a lot like our Laplacian of Gaussians. It's not actually the same if you sort of plot these things out. They're like very minor differences, but in practice, they're doing very similar things. So what this is going to do is basically look for parts of the image that are in between a very specific band of frequencies. And this is cool because we can now look for sort of really fine detail in the image and separate that out from lower frequency components or sort of mid-frequency components that might correspond to like larger edges or bigger changes in the image. So in practice, when we apply our difference of Gaussian filter, I like it because it's a dog filter. This is when we do the difference of Gaussians with a standard deviation of 1 subtracted from a Gaussian with a standard deviation of 0, which isn't actually a thing. It's just the original image. We get a lot of this really fine detail or sort of these fine edges in the image. If we start increasing this a little bit, this is a standard deviation of 2 subtracted from a standard deviation of 1. We start getting, so as we start increasing, we're basically not looking as much at the really fine detail. We can sort of go back and forth between these. So in this one, we see a lot of the sort of little edges in the leaves and stuff like that. In this one, we're starting to pick up on some of the larger edges in the scene. We also, as we start transitioning to larger and larger frequency changes, we get more of the color information in an image. So we're going to keep going up. Difference of Gaussians from standard deviation of 3 minus 2 and of 4 minus 3. And so our last version of this that I kind of ran on this image at least, we're filtering out all of the like sort of really low frequency information or sort of really high frequency information. And we're just left with some of these really broad low frequency changes that are happening in the scene. So the bicycle has just become sort of a few of these broad strokes. And all of sort of the detail from the dog is kind of filtered out. And we just get the really major changes that are happening, sort of these color patterns and stuff like that. So in general, these difference of Gaussian filters are kind of cool and useful for separating out the different components of our image into high and low frequency information. And these are going to come up again a lot when we're talking about feature extraction as well, because often it's important to kind of be able to do this decomposition and be able to separate out these components and process them in some way. So we're just going to keep talking about different ways to find edges, because finding edges is so important that this is like all people did in computer vision for like 40 years, was just figure out new ways to do this. We talked about how we want to find basically extreme points in our gradient. And probably a lot of you guys were thinking, like, why don't you just square this stuff? And then instead of being positive and negative, we can just look at the magnitude. That's a great idea. Let's just do that instead. So instead of doing all this weird second derivative stuff and like looking for these zero crossings, and the second derivative is really sensitive to noise, so that's annoying. Let's just take our gradient of the image and then look at the magnitude of this gradient at different places in the image. That's a great idea. So again, we already have these Sobel filters that we talked about before, and they're going to be our estimates of the gradient of this image. And so you might sort of think like, okay, and you guys are doing this for your homework too. So if we run these Sobel filters over the image, and then we can take the magnitude of sort of the vector, basically take the x and y direction, like components, square them and add them together. And this gives us sort of this kind of nice image of like where there might be some edges in this image. So we might kind of think like, okay, this is like pretty good. Maybe this is good enough. We're not done yet. So in particular, when we're talking about images and we're talking about edges, we don't really want like this kind of fuzzy approximation of like where the edge might be in the image. So if you actually had to go in and like say, okay, where are all of the actual edges? Like this is a pretty broad boundary here. And what you really want to figure out is like, where's the actual line that's like right in the middle of that edge or something. And so what we really want is like some kind of little line drawing of our image where we actually figure out sort of specifically where the edge boundaries are. And so our magnitude of gradient operation that we talked about before is going to be kind of the first step in this process, but it has a few issues with it in terms of like producing these really wide boundaries for these really strong, large edges and producing sort of a lower response for some edges that may be sort of just as prominent, but maybe sort of smaller edges and things like that. So what we really want is like if you gave this image to like someone drawing with a pencil, what marks would they make with that pencil to kind of estimate where the lines are in the image? So we're going to talk about canny edge detection, which was sort of the most successful way of doing this that we have up till now, or a really common way of performing this task. And in particular, it's not just sort of doing this gradient, but it's doing a bunch of post-processing afterward. And it's this image pipeline. And people in computer vision love image pipelines. So it's important to start kind of getting familiar with these image processing pipelines and seeing what their whole deal is. So in particular, we're going to be doing a couple operations that you guys should be pretty familiar with. We're going to smooth the image, and we're going to calculate the gradient. And we're going to calculate gradient direction and magnitude. So again, in most image processing things, you're going to have some convolutions in them. In this case, these two steps are our convolutions. We're going to be doing this smoothing and these gradient calculations. But then we want to do some kind of estimate based on this result that we get of where the actual edge is in the image. We don't want sort of this fuzzy boundary. We want to find kind of the single pixel line of the center of this edge. So to do that, we're going to be doing some non-maximal suppression, where basically we look at the response of our gradients and we figure out where the strongest response is, and then get rid of the other responses that aren't as strong. And then we're going to do some sort of connected component analysis and some thresholding to make sure that we only end up with a few edges. We don't want basically all of the high frequency information in the image. So we can do some kind of thresholding to get rid of some of the noise and stuff going on in the image that we still have left over. Even after we do this smoothing, we still probably have some sort of noise components that made it through that process, and we want to get rid of them. So this is our general overview of what canny edge detection is going to be, and we'll talk about kind of each of the steps individually. So in particular, there is this cool website where you can try out, well, if I do that, it brings up that little thing, but as soon as that goes away, there's this cool little website that you can try out a canny edge detector on your images and just kind of see what happens. But this is the process. The first thing we want to do is smooth our image, and we already know how to do this. We use these Gaussian filters. Then we want to do our gradient calculations, and in particular, we want the gradient magnitude and direction. So we're going to be using these Sobel filters that we talked about, and you guys are going to be doing this in your homework too, so it's good. You're kind of building out a couple steps of this process. We're not actually going to implement the whole canny edge detection process. That is a really common project to do for computer vision, but I would rather have you guys be doing neural network stuff, basically. So we're going to skip that and get to neural networks faster, which is fun. But the next portion is basically doing this Sobel filtering of the image to get these gradient magnitudes and directions. And then we want to perform some kind of non-max suppression. So in particular, for some area of response in this gradient magnitude image, we want to just get sort of a single pixel line that runs through that is sort of the center of the edge. So if we look at just one small component of this, just kind of this little handlebar area of the bike right here, we have, for most of the pixels in this image, they're all going to have a pretty similar gradient direction. So the gradient might be pointing either this direction or in the opposite direction. But in general, they're all kind of along this edge. So they're going to have a similar component of their gradient. And from that gradient, we know that the edge runs perpendicular to the estimate of that gradient. So what we want to do is just figure out what the strongest pixels are along the direction that we know, or that we sort of think is probably the edge. So in particular, for every pixel in this image, we're going to look at its neighbors both in the direction of the gradient and in the direction of the opposite of the gradient. So we want to find components that are strong along this edge, which means that we want to eliminate components that are weak that kind of go side to side in the same direction, or that go sort of side to side perpendicular to the edge. So this pixel in particular, the pixel to sort of its lower left that's in the direction of the gradient has a lower response than it does, so that's fine. But this pixel here actually has a higher response than this pixel. So during our non-max suppression, we're going to look at those two pixels and say, OK, my neighbor in the direction of the gradient actually has a higher response than me, so I should set myself to 0. And then we're going to look at a bunch of other pixels in the scene. And so for this pixel, we're going to look at its neighbors and see that both of its neighbors actually have a lower response than it. And because of that, we know that we can preserve that section of the response as being basically a correct response. So it's sort of larger than all of its neighbors in the direction that isn't the edge. So in particular, this pixel here might be stronger than this pixel in terms of its level of response, but that is still consistent with the idea that the edge sort of runs along this line in the image. So this pixel can, be stronger, but this pixel can still be part of the edge. But in particular, we don't want pixels sort of to the left and right of the edge that are weaker than the actual pixels along the edge still showing up in our final image. So after we run non-max suppression on this image, we end up with just sort of this single pixel boundary that runs through this location in our response map. And that single pixel kind of line goes in the same direction of the edge. And in terms of looking at where the gradient is pointing, we don't have any responses in the direction of that gradient that are weaker than this single pixel boundary that we have. And in practice, when we're doing this lookup, let's see if we get, well, it's fine. In this instance, it actually worked out pretty well because our gradient direction is kind of at 45 degrees. So when we look from this pixel in the direction of the gradient, we kind of end up right at this pixel. And we can do that lookup pretty easily. There are a few ways of actually doing this in practice. So one way that we can imagine doing it is just binning the gradients into different angles. So in particular, there's sort of like, there's only 8 pixels that you can look at in terms of direction. So if the gradient falls in any sort of direction that's like, more or less horizontal, we're going to look at the 2 pixels to the left and right. If the gradient falls in any of sort of the angles that might be kind of construed as diagonal, we're going to look at the pixels that are on the 2 corners. If the gradient is some sort of like vertical, more or less vector, we're going to look at the top and bottom pixels when we're doing our non-max suppression. So that's one way of doing this non-max suppression when the gradient direction might not be exactly toward a pixel that is your neighbor. The other way of doing it is just doing some kind of interpolation. So you can imagine that this gradient, is actually pointing pretty close toward this pixel. But if we're actually pointing, let me do this with the pointer because it's going to be a lot easier. If we're actually pointing kind of in this direction, you might end up wanting to look at a pixel that sort of falls in between these two pixels, or at sort of a location in the image that falls in between these two pixels, and saying, what is the response of this location in the image so I can figure out if I should suppress this area. And fortunately, we already know how to do that too. We just use one of our interpolation techniques. So nearest neighbor interpolation would be kind of doing the thing that we talked about before, where we bin the gradient in different directions. And doing linear interpolation would be this thing where we basically project our gradient out in a direction and then try to interpolate in that direction what the response would be of our features that sort of fall in between maybe a couple pixels. And either one of these two strategies will give you some kind of results. And then it's just like a bunch of little knobs that you can tweak to kind of make your edge detector perform a little bit better. So just one of those things to think about. And another, my computer's running out of battery. Another thing to kind of think about as a possible application for doing some of this image interpolation stuff that you guys are doing for your homework right now. So does non-max suppression kind of make sense, this process that we just went through, everyone? OK, this is a super important concept just in general. A lot of image processing basically is looking for responses to some kind of feature extraction or some kind of process, and then figuring out what the right response is. And usually when you're trying to figure out what the right response is, you're going to do some kind of non-max suppression. Because in general, images, especially when you're doing these convolutions, if you run this convolution, you're not just going to get a single response right at the place that you care about and then no responses anywhere else. What you're actually going to get is one response that's really strong, but then a bunch of responses around it that are also pretty strong, and then maybe some more responses around them that are a little bit weaker. And you have to kind of figure out what the right component is of this feature map that you're going to get, or this map of responses that you're going to get. And it's not always super easy. This is another thing that kind of we'll talk about when we start talking about detection too, where we have to do this non-max suppression, where there's this question of, say you detect, say you run a detector on an image and you detect two people in that image. Are there really two people in that image, or is it detecting the same person twice? And the process that we're going to use to sort of try to resolve that is non-max suppression again, but in sort of a little bit different fashion. So this is a concept that comes up often, and you actually will be implementing this for your next homework, but using a different kind of feature map and a different kind of non-max suppression. So just kind of keep in the back of your mind that non-maximum suppression is important for canny edge detection, but it's also important for a lot of other computer vision applications. Question?
How do you decide?
Because we can calculate it. So we have our Sobel filters, and they're going to calculate the component of your gradient in the x and y directions. And just using those two vectors, you can calculate using trigonometric functions what the direction of the gradient is. And you'll actually be doing this in this homework, I think, where you calculate magnitude based on squaring these and adding them together. And you calculate direction based on the arctangent of the y component divided by the x component, basically. So you have basically two perpendicular lines, and they have different magnitudes. And then you can use the arctangent to figure out if you added those two lines together, what direction would that vector point? Yeah?
When you do the allowed, instead of
Maybe. So for canny edge detection, the idea is you want sort of a 1-pixel edge. But you can imagine that maybe edges are thick. I mean, so yeah, in particular for canny edge detection, we want all edges of all kind of width just to be shrunk down into this single pixel boundary. But in practice for non-max suppression, like maybe sometimes you might want that. And it doesn't always like, let's go to our actual edge. You know, like these two pixels are kind of next to each other. So it's not like eliminating just everything except for kind of the pixels in this diagonal. And that's because the gradient, you know, from here goes over to this pixel and to this pixel. And the gradient from this one kind of goes to this pixel and this pixel. But there's no real interaction because the gradient doesn't kind of point just in the x direction between those two components. So there is kind of this little step thing that ends up happening. But it's, yeah, you probably, at least for this task, don't really want sort of a 2-pixel boundary. But if you did, you could imagine kind of modifying your non-max suppression to take that into account and maybe to somehow factor that in. Yeah. So you know, in general for this image, all of these pixels are going to have very similar gradient directions. They're going to have different gradient magnitudes. But yeah, you're going to calculate basically the gradient for every pixel. So I just kind of have one arrow up on this screen. But each of these pixels is going to have, and in particular, the pixels that are down here are going to have gradients pointing upward. And the pixels that are down here are going to have gradients pointing in this direction. So they're going to be having different gradients, but they're generally going to be in the same direction, modulo sort of sign flipping. And they'll have different magnitudes. And the magnitudes, actually, you can tell what the magnitudes are because they're represented just in terms of the responses in this image. And actually, I think I was wrong, actually. Probably all of these pixels will have gradients in the same direction, roughly. They'll probably all have, I forget which part of the handlebar this is. Let's see. So if this is this part of the handlebar, I think the handlebar is black, and this part is, you know, not as dark. So the gradient is going to be pointing from the handlebar towards the part of the image that isn't as dark. So all of these vectors are going to be pointing kind of toward the upper right portion of the image. And then they'll all have different magnitudes, and that's already displayed, basically. Everyone pretty comfortable with non-max suppression? So what we end up getting out of this is a much thinner version of the response map that we had before, where we have kind of these individual pixel boundaries. I don't think I ended up kind of zooming in on this picture, but we see that, you know, now we have a lot of these kind of thick, broad edges that we had before just kind of mapped down to individual pixels. And that's pretty cool. But we're still not done yet. So now we're going to go through this thresholding process. And in particular, we want to figure out basically which of these pixels are real edges and which of these pixels are just kind of noise or like some random stuff going on in the image or just like nothing. And so we want to pick some thresholds for figuring out where the real edges are. And we're not just going to pick a single threshold for reasons that we'll talk about right after this slide. We're going to pick 2 thresholds, and we're going to split our pixels up into 3 different cases. We're going to have strong edges where our response in this response map is stronger than some big threshold. We're going to have weak edges where the response isn't stronger than sort of a large threshold, but it is stronger than some smaller threshold that we set. And we're going to classify these as sort of weak or like intermediate edges that we're not quite sure about yet. And then if our response is smaller than our lowest threshold, it's definitely not an edge. It's just like some random part of the image that we don't care about, and we're going to forget about it. So why do we have these 2 different thresholds that we're going to use for the image? Because we want to start connecting some of these edges together. And in particular, if we just look at kind of the strong edges, there are, as we talked about before, there are going to be some noisy parts of the image where we might think there is an edge where there isn't an edge. But there's also going to be some noise in the image that makes edges maybe look a little bit less like edges in some places, and we want to be able to get around that. And a way of getting around that is that sometimes, there might be a real edge in the image, but there's some noise that doesn't make it as prominent, so it'll kind of look like a weak edge. And we're going to include those weak edges. We're going to include those weak edges in our detection if and only if they sort of connect to some of these strong edges also. And so there are a few different ways of doing this, but sort of the most simplest one is, all of the strong edges, they're bigger than this threshold, so we know that they're part of real edges in our image. And then any of the weak edges, we're just going to look at their 8 neighbors, sort of the 8 closest things to them. And if any of those are strong edges, we have a pretty reasonable expectation that that weak edge might also be part of an edge. So we'll just add it into our full set of pixels that we've decided are edges. And this is kind of the last step in the process, and we get this nice little picture where instead of sort of this these thick edges and kind of this grayscale intermediate between black and white, sort of these large fuzzy edges, we're just going to have all of the pixels either be 0 or 1 in this image, where 0 means that it's not an edge, and 1 means that it is an edge. And we end up with a pretty reasonable approximation of some of the edges in this image. And again, so here's our sort of algorithm again. And we have a lot of tunable parameters in this algorithm, not even sort of in terms of the algorithms that you might pick for doing non-max suppression, but we have things like what is the sigma that you're going to use for doing this smoothing, what are the thresholds going to be, and then we have some more kind of design decisions, like how are you going to connect together the different components of edges in your image, and how are you going to do things like non-max suppression and stuff like that. So this is kind of a general overview of the Canny edge detection algorithm. When you actually implement it, you have to start making a lot of these decisions in terms of what you want these thresholds to be and what you want these little design decisions to be and stuff like that. And a lot of these are kind of tunable for a particular image. So you might have an image where you need slightly different sigmas and slightly different thresholds to get out the edges that you actually care about for that image compared to some other things. Here's a pop quiz really quickly. We have the sigma component down here, which is how much you're going to smooth the original image. Who can tell me, or just discuss for 2 minutes, what increasing or decreasing that sigma parameter will do to the eventual edges that we detect? Go. So if you use a larger sigma, what will change about your edges? And if you use a smaller sigma, what will change about your edges? Discuss. I'll try to find. Okay, who's got the answer? Anyone? Yeah. Okay, so you'll find fewer edges. Anyone got anything else? Yeah, okay. Anyone know anything about the kinds of edges that you'll detect with these different values of sigma? Yeah? Yeah, so you're going to detect sort of the bigger edges in the image. Again, it's kind of this frequency thing that we were talking about, basically, where with higher sigmas, we're going to filter out a lot of the high frequency information, and we're not going to detect, the edges that exist between the little leaves in that tree. We're just going to detect, maybe the edges of sort of the bicycle or something like that, sort of the bigger, lower frequency edges in the image. So we have our little demo thing. Let's pick pick a good image. And we can sort of see what happens as we go through different steps of this process. So we have our input image. We have some Gaussian smoothing. We have our gradient calculations. This one will also show you the gradient directions. So this is the x component of the gradient and the y component of the gradient. We have our non-max suppression, and we have our thresholding that happens. And in particular, we can say, OK, when we set our sigma to be really low, we have a lot more of this fine detail, but as you guys kind of mentioned, a lot more of maybe noisy edges that kind of come through. And as we increase this sigma more and more, we only get some of these really big edges in the scene, some of these components that sort of correspond to low frequency changes in the image. So if this is our original image, the edges that we kind of end up with a really high sigma are like, these big edges that correspond to the boundary of the mountain, or sort of this big seam running down the middle. I don't know, ridge, I guess, whatever that's called. I should know this kind of stuff. So you guys can play around with this, and you can also play around with basically changing these different threshold values. So again, there's this like high threshold that we talked about, where anything above the high threshold counts as a strong edge, and then there's this low threshold where everything above the low threshold counts as a weak edge and only gets added if it's connected to a strong edge in some way. So it's just like a fun little demo that you guys can play around with, and there's a link to on the slides, and maybe I'll put a link to on the website, just so you can kind of like, since we're not actually going to be implementing this ourselves, you can get a little bit of a feel for canny edge detection if you want. So this is kind of the input and the output edges that we get. And again, it's like super highly tunable depending on the image and depending on what kind of information you want to pick up from the image, et cetera. So we talked about a lot of different ways to find edges so far. But edges are not all that we might care about in an image. In particular, we're going to start talking about features of images and how we detect features and what makes a good feature, and some different ways of doing feature extraction from images. So in general, features, don't pay attention to the images here. They're just kind of like cool little things because I had to fill in the slide with something. So features are basically highly descriptive regions of the image. And in particular, we want to basically find places in the image that have some sort of meaning. So things that are useful for maybe matching up different locations between two images. I don't know what happened. Do that. We're back. So features are going to be useful for doing a bunch of things like matching up different locations that are the same in two different images, doing things like recognition or object detection. They're useful for a bunch of different applications that we care about. So what is a feature? What are things that make up a good feature? What do we actually care about? So if we want to perform some of these tasks, like if we want to stitch together a panorama, or we want to find location, like say we're given an image of some object like this bottle, and then we're given another image where that bottle exists in that image somewhere, and we want to find the bottle in sort of this larger image. We're going to want some kind of features. We're going to want something that kind of corresponds to some meaning in the image, and in particular, especially for things like objects, if we want to basically find this bottle in some large part of the image, we want a patch, or we want some descriptor of this image, of the thing that we care about, where we're going to be able to find it really easily when it actually exists in our image, and we're not going to get confused with other patches that might look sort of similar, or other features that might look sort of similar. So for panorama stitching, there's a really specific example where basically we want to figure out what parts of two different images are the same, what parts kind of correspond to each other. So we want to find patches that we can easily find in another image that are actually the same place, and patches in the image that aren't going to get confused for other parts of the image and might sort of confuse this stitching process that we're doing. So good features are going to kind of be unique. We want to find, basically, if we're talking about sort of an image patch as being one of our features, we want to be able to find the same image patch when it is actually the same really easily in another image. And we don't want to be mistaken for sort of a different image patch if it's not actually kind of the same thing that we're looking for. So we're going to formalize this notion a little bit in terms of figuring out how close are two different patches of an image from each other. And often a distance metric that people kind of use is sum of squared differences. So if we have two image patches, or basically just two images, I and j, we can imagine just summing all of the pixel locations in those two images, or summing over all of the pixel locations in those two images, and figuring out the distance between the feature responses of those two locations, or sort of the function responses of those two locations. So again, remember that images are just kind of these functions, and we're just measuring what are the difference between these two functions. So, I of xj is just the pixel value at x and j in image I, and this is the pixel value at x and j in image j. And we're just going to subtract them from each other and square this. This is just kind of what you think of as like square distance or Euclidean distance or whatever, but without the square root. So we want to figure out some way of finding unique patches, some way of finding some patch in an image that isn't going to get likely confused with a different patch in a different image. And so we have these two images that we might be trying to stitch together, and we want to find patches that match to basically exactly one spot in the other image and aren't going to get confused with different spots in that image. So we can think about maybe our image patch is going to be the sky. Well, that's really bad, right? Because any other place in the sky, this image patch is going to match really highly with. It's going to have a really small sum squared difference. It's going to have sort of a really low distance from any other sky patch. Edges, sort of that might correspond to this little cornice of snow, are all right in that they have variation in one direction. So if you shift this image patch sort of in the direction opposite that the edge goes in, it's not going to match very well. But it could match basically any other patch that's along that same edge. As long as you're just sort of sliding along that edge, it's going to have a pretty low sum of squared difference. Corners are the thing that we really want. And this kind of makes sense if you've ever played around in Illustrator or Photoshop or something, and you have two images. You often kind of look for corners to match them together because they're this very specific point, and you can kind of tell if they move in any direction because you have these two edges that come together. So if you're off by a little bit, either one of those edges isn't going to match up or the other one of those edges isn't going to match up. So we want some way of kind of formalizing this concept of finding these corners. There's some way of formalizing this concept of finding patches in the image that have a low distance between other patches in the image. How can we sort of find these unique patches? So one thing we could think about is just we're just going to loop over every little patch in this image and calculate the distance between that patch and every other patch in the image. And if we did this, we would find really unique patches. We would find patches that have a really high distance from every other patch in the image. And our hope is if we find a patch in this image and it's different from all of the other patches in that image, hopefully that means that it will also be different from other patches in other images. So basically, if we find a patch that's kind of unique in this image, maybe there's some hope that it'll kind of be globally unique in terms of other images as well. And that would be a good thing. So that's the thing that we really care about, is finding kind of globally unique patches. But we've already started basically saying, OK, maybe we'll just approximate that and find patches that are unique just to our image. But that still is going to involve a lot of computation because we'd have to basically calculate the distance between every small location of our image with every other patch that might exist in this image. And in practice, these image patches are going to be pretty small. They're going to be on the order of like, 7 by 7 pixels or 10 by 10 pixels or something like that. But it's still, like there's a ton of potential like possible image patches in this image. And it would be a lot of work to do this whole calculation of comparing them to every other possible image patch. So instead, what we're going to think about is this notion of autocorrelation, which is basically how well does the image, or does the little image patch that we're talking about, match a shifted version of itself. And in particular, this is sort of a measure of self-difference, or a measure of like, if you take this image patch and you move it around a little bit, do you quickly get large changes in this distance function that we just talked about for image patches, or is the patch kind of always pretty close to itself? And this will maybe be some approximation of how unique this patch is globally. So now, instead of basically this distance function where we're talking about two different image patches, we're just going to calculate the distance with small variations in location between an image and itself. So this is the image response at a location, and this is the image response shifted just by this small vector d. And we're going to talk about a weighted summation of how close an image is to shifted versions of itself. So if we're talking about this notion of self-difference, and we're looking again at these little patches that we already discussed, when we have the sky and we sort of shift it around and compare it to itself at different locations, we have a really low self-difference kind of everywhere. So obviously, if an image patch is right on, if we sort of don't shift it at all, if we're just kind of comparing it to itself, we're going to have a zero component in terms of how different it is from itself. If we shift it just a little bit, for this sky image, we still have basically two images that are basically blue everywhere. And the same is true if we shift it in the other direction. We have this these two images that are just kind of blue everywhere. They're always going to have very similar responses in terms of their functions, so their self-difference is going to be really low. When we have this edge, and we're talking about the self-difference of the edge from itself, obviously, again, when we haven't shifted it at all, it's going to have a very low self-difference. If we shift it in terms of a direction that is perpendicular to the edge, we're going to start getting some differences. So in particular, this snow overlaps this blue in the background, and that's going to give you, or sort of a, gray or something in the background, that's going to give you some component of self-difference. But when we're shifting it along a vector that is parallel to the actual edge, we get very low self-difference again, because we're still just comparing kind of components of snow with each other and components of the background with each other. So in general, edges are still going to have pretty low self-difference overall, because they have this one component along which they have very low self-difference. So even though sometimes they're kind of different from shifted versions of themselves, they also have components where they're pretty similar. Again, corners, we have this cool sort of property where when you shift this corner in any direction, you're going to have one edge. Since you have these two edges coming together, you're always going to have one edge that is sort of shifted off of another edge, and you're going to have some large component of self-difference kind of right away. So again, when the two filters are sort of right on top of each other, you just have this perfect match, and your self-difference is really low. But then as you start going in any direction, we already see that we have this component of this mountain in one image overlapping components of sky in the other image, and this distance function is going to start getting large pretty quickly. So corners end up having pretty large components of self-difference, which is really nice. And this means that instead of looking in sort of the entire image for patches that are kind of unique, what we can really look for is just patches that are sort of unique to themselves or have sort of high components of self-difference. And here's just like sort of a little plot of what we actually mean by this concept, where if we have this corner and we don't shift it at all, obviously we're going to have very low self-similarity, or sorry, very high self-similarity, very low self-difference. But then as soon as we start shifting in any direction, our function, our distance function, is going to start getting pretty high pretty quickly. I'm sorry, I don't know why my laptop is doing this. With the edge over here, as we shift along a single axis, we're going to have a really low distance function. And then if we shift off of that axis at all, we're going to start having a high distance function. But there is enough of sort of a low component here that we can kind of eliminate this just by sort of summing all of these together. And with this little sky patch over here, we basically have this low self-difference function kind of over the entire space, where anywhere you kind of shift it, it's going to match pretty well with itself. So keep this in mind for next time, and we'll finish up on talking about how we find corners. And yeah, see you guys later.